Hello everyone, my name is Marcel Steinbeck, I'm from the University of Bremen, Germany, and today I'll present our results regarding Javadoc violations and their evolution in open source software systems. We all appreciate well-documented software. I mean, I've never heard someone saying that code is too well documented and thus is not maintainable anymore, right? Anyhow, I claim that each of us maintains at least one project where he or she has to admit that it is not adequately documented. There are many reasons for insufficient documentation. Two things that first come to my mind are time pressure and the fact that there is no strong connection between documentation and code. In a sense, improper documentation of source code has a lot in common with code smells. Both may have a negative effect on software maintainability. Therefore, just like code smells, source code documentation is an interesting field of research. So we were interested in analyzing violations to source code documentation, in particular Javadoc violations. We chose Java as subject language because there are already a number of good tools for analyzing Java, and Java has been subject of a variety of research studies in last years, making it easier to compare results with previous studies. Also, we were interested in examining the evolution of Javadoc violations, that is, tracking findings through the change history of software systems. Before presenting our research questions, I first need to talk about Javadoc components. Each Javadoc string can be decomposed into different components, for example, a general description, parameter components, return components, and so on. The components that can be contained in a Javadoc comment depend on the type of the documented source code element. Javadoc components can be distinguished into three categories: recommended components, optional components, and incorrect components. Recommended components are those that are generally expected when reading Javadoc. Optional components are those that add additional metadata, for example the author of a comment, the version, and so on. Finally, incorrect components are components that do not match to the type of the corresponding source code element. While incorrect components are clearly determinable, recommended and optional components are not. Our classification of recommended and optional components is based on our own experience in software development, but we also considered warnings and errors reported by the Javadoc export tool. Here you can see all source code elements that can be documented with Javadoc, as well as the recommended components. Note that we did not analyze the documentation of packages, because we found that almost all projects did not document any package. Also, it is not clear whether a package with a documented parent package should also be documented. With this in mind, our research questions are as follows. Are certain types of code elements, such as classes, interfaces, and so on, more likely to have Javadoc violations than others? The next question is, are certain Javadoc components more likely causing Javadoc violations than others? And our final question is, how long do Javadoc violations live? So, how did we analyze Javadoc violations? We processed all code elements and first checked whether there is a Javadoc comment associated with them. If not, we found a violation of type missing Javadoc. If there is a Javadoc comment, we then checked whether all recommended components have a meaningful value. What a meaningful value is will be discussed in the next slide. If one or more recommended component has no meaningful value, we found a violation of type incomplete Javadoc. Also, we checked whether the comment contains any incorrect component, resulting in a violation of type incorrect Javadoc. While missing Javadoc is mutually exclusive to incomplete and incorrect Javadoc, comments can of course be incomplete and incorrect at the same time. Now, let's talk about meaningful descriptions. If a component is missing, like for example parameter A in the first listing, or have no description like parameter B, a violation can trivially be assumed. However, checking for meaningful descriptions in text is practically impossible. Thus, we decided to be as indulgent as possible and allow any description with at least one character. While processing Javadoc comments, we also handled some special cases. As already said, we ignored Javadoc of packages. Also, we ignored test code, private elements, and accessor and mutator methods because their documentation does not seem absolutely necessary. Another special case is inheritance and interfaces. For example, if an interface declares a method with corresponding Javadoc, classes implementing this interface do not need to document the implemented method. Likewise, Subclasses do not need to document overridden methods. Last but not least, we implemented an advanced analysis to extract unchecked exceptions that are explicitly or implicitly be thrown by methods. In our study, we expected not only checked exceptions to be documented, but also unchecked exceptions. In our study, we analyzed the entire history of 163 open source projects hosted on GitHub. As you can see, on average, we analyzed a period of over 1,800 days, which is about 5 years, and a period of over 180 revisions. The project with the longest period in terms of days is Dr. Java, with over 18 years of history. Fun fact, Git was released about 16 years ago, so Dr. Java's repository must have been migrated from another version control system. Now, let's have a look at our results. Research question 1 and 2 do not relate to software evolution. Thus, to answer these questions, we analyzed only the latest revision of each project, as it is the most up-to-date version of a system accumulating its entire evolution. On the left you can see the total number of affected source code elements separated by their visibility. Not surprisingly, methods are more likely to have Javadoc violations, because in general, methods are one of the most frequent elements among all types of source code elements. On the right you can see the ratios of the affected source code elements for each project as box plot. What surprised me was that, on average, about 95% of all constructors of a project are affected by Javadoc violations, closely followed by methods with more than 80%. Also, I was surprised that annotations have an average ratio of 0%. However, this results from the fact that most projects don't implement their own annotations. If we leave out projects without annotations, the average ratio is about 60% though. With regard to research question 2, we gathered the number of affected Javadoc components both in terms of absolute and relative numbers. As you can see, about half the code elements on average have no Javadoc comment at all. Also, throws components have a relatively high average ratio, which most probably results from our analysis of unchecked exceptions. Interestingly, descriptions and incorrect components have a relatively low average ratio. To answer research question 3, we tracked the evolution of over 400,000 violations. The results can be seen as box plots here. When seeing the results at first, I was wondering why some violations have a negative lifetime. But first things first. According to our results, violations on average live about 800 days, which is more than 2 years, and about 200 revisions. So why do we have violations with negative lifetimes? I examined some of our results and found several situations like this where commits in a linear history don't have consecutive dates. In Git, commits and accordingly their timestamps are created decentralized. Also, one can cherry-pick commits from other branches, so I guess this is an artifact of some sort of strange commit and push order. Anyhow, in this example only Alice Purcell can tell what happened here. We also gathered the evolution separated by source code elements and Javadoc components. For the sake of better comparability, we also plotted the means as green triangles. For example, according to our results, classes are affected by Javadoc violations for about 800 days median, or about 1000 days mean. Although we found several statistically significant differences, there are no unusual strong deviations in these results. So here are our conclusions. Constructors are mostly affected by Javadoc violations, followed by methods and fields in relative terms. Annotations, interfaces and enums have a ratio less than or equal to 0.5, meaning that classes, constructors, fields and methods are more likely to be affected by Javadoc violations than being free of them. Interfaces are less affected by Javadoc violations than classes and enums. This is most probably because interfaces serve as a specification. Missing Javadoc is the most frequent kind of violation. Actually, about half the code elements have no Javadoc comment at all. This is followed by throws components. Param and return components are almost equal and well below throws components. We found only few cases where a description is missing, and we also found only few cases of incorrect Javadoc components. According to our results, Javadoc violations live rather long, and there are statistically significant differences in the lifetimes of source code elements and components, but there are no unusually strong deviations. So what are threats to validity? We only examine Javadoc comments in open source Java systems, thus we cannot generalize our findings for other programming languages and closed source applications. Also, our sampling of projects might be biased. We decided to handle different kinds of special cases. For example, we expected unchecked exceptions to be documented with Javadoc. Also, our static analysis of potentially thrown exceptions may yield incomplete results. We accepted all kinds of descriptions as long as they are not empty. This is a rather weak criterion for checking the quality of descriptions though. Finally, we cannot say how active violations evolve in the future. In particular, we did not exclude very recent violations from our analysis, which may affect results. So in general, our findings regarding the number of violations and their lifetime is a lower limit. Thank you for your attention, and do you have any questions?